Invited me to come along and talk to you. I was on holiday last week, so I pulled some things together, and I thought what I'd do would give some sort of perspective on modelling in industry and why we think it's important, and try and talk about that a little bit, and then talk at the end about some problems which I'm still worried about. So why do we do modelling? Certainly in industry, there's three main things really: to build our understanding, to interpret experimental results, and I'll give one or two examples of this in just a second, at least just an overview, and to aid optimization. So for example, we were focusing on looking at developing new types of liquid crystal display, and these were bistable displays, and at the start we knew they were bistable, we knew how to make them. It seems actually fairly, with some experience now, fairly easy to get bistability, but then you have to be able to switch. You want the switching voltages to be reasonable. It's no good if you've got to use 90 volts to switch a liquid crystal cell or a liquid crystal display. So you want to know about switching. How do things switch? What controls the sort of voltages you need to apply? What are the parameters that are important? As part of that, you want to be able to investigate the cells you've made, and then finally, having made some cells and have hopefully some idea about how to switch them, how to make them so they're switchable, how do you optimize them so you get really good optics, so you can get a good display that obviously Hewlett-Packard in this case would then want to produce or sell on the market or develop as a commercial thing. So that's the other thing. I work for Hewlett-Packard Laboratories. We're the corporate research laboratories. So Hewlett-Packard has a number of divisions, some making laser printers, some making inkjet printers, some making laptops, and so on. And each of those parts of the company, they have some research and development. What that's doing is looking at the next product, the next two products, how are things going to develop, how are they going to continue competing in the marketplace. So that's the sort of what we call, each part is a division, so that's a divisional research and development. But in addition to that, Hewlett-Packard and Hewlett-Packard still, to some extent, although not as much as they used to, fund a corporate research arm where we're tasked with developing new products, new ideas, things that might be used, say, in 5-10 years' time. And so we have some flexibility to do what we want, and some scope for that over time, but we have to be able to justify what we're doing in terms of, in this case, printers. We make a lot of money with printers, we sell a lot of printers, but in some time frame it may be that printers go away. People don't print things anymore, and we're already seeing some of that. People using book readers and so on, rather than buying printed material. And so if that's going to happen, if printers are going to go away, then obviously Hewlett-Packard wanted to be able to say, well, we can use or develop appropriate displays that are good for reading, therefore higher resolution, work well outside, so they've got good optics, good reflective color optics, and so on. So a whole range of things, a whole range of reasons why we'd be interested perhaps in developing our own liquid crystal technology. Of course, part of the problem with that is, as we're developing the technology that's already there is also developing as well. So it's a bit of a race. But that's why we ended up working on liquid crystals initially. So we've got some cells. We want to be able to understand how they work so we can make them better. We want to be able to experiment with them and interpret those experimental results, and also perhaps at a slightly later stage we want to be able to optimize them so we get good switching, good optics, and so on. So I'll just give an example of those things. So here's the challenge really in terms of a plastic liquid crystal cell. So here's a cell that we've made, and it's 0.3 millimeters thick altogether, and this is more or less to scale, and the little green line is the bit the active part, the liquid crystal, and we want to be able to understand what's happening to the liquid crystal in that cell. And so part of it then is doing some experimental measurements, trying to interpret those results. The liquid crystals are too small, we can't see what's going on under a microscope. Typically for the bistable cells, as I'll talk about in a moment, length scales are typically about a micron period and 4 or 5 microns thick. So we can't just look down the microscope and say, oh yes, that's what's happening, or get much of an idea. So we want to be able to probe the cell, and this is one way of doing it. So we have a laser, we have a polarizer and a wave plate, which means we can set up some polarization condition, and then we shine that light through the cell, which can rotate about vertical axis there, and we measure the light that comes out. So we know what sort of polarization we put in, we measure the light that comes out with a polarimeter, and then the question is, given that information, can we deduce what the liquid crystal is doing inside the cell? And it turns out that that's actually quite a hard problem, a difficult inverse problem, and we did some work on inverse problems with people at Manchester University, and this is just an example of the sort of fits that we were able to get in terms of the coloured lines and then the fit for the data. So the C's are the calculated from the model, and the fitting, and the D is the data. So you can solve that sort of problem, but actually it's not straightforward. It's a difficult inverse problem, and we spent some time doing that. And we want to do that because we want to understand what's happening inside the cell. For example, what's happening at the surface, what's the surface tilt, what's the surface interaction like, and so on. So that's one thing. Optimization, well, we can calculate the optics as light passes through the cell, and this is just a simple hand cell. I guess most of you probably know what a hand cell is, but we've got on one surface we've got more or less planar alignment, perhaps a slight pre-tilt, but in some general uniform direction, and on the top surface we've got homotropic anchoring, and the liquid crystal is obviously bending and splaying to match those boundary conditions. So that's just a simple cell, but we could do some optics calculations. On the right then we've got the dark state, if the liquid crystal is all homotropic. On the right hand side we've got the sort of optics you get if you just have a Han cell. And it's not symmetrical because, you can see if the tilt is this way, then a light beam coming in this direction actually sees different arrangement than light from this direction. And so that's why we see the asymmetry. But then the question is, what can we do to optimize that? What can we do to make that better? We can add a wave plate as well. We can do extra calculations and try and improve the characteristics of the cell. So that's another thing that we're interested in. And finally, understanding better what's going on inside the cell, doing some actual liquid crystal modeling. The initial model we developed was a director model, a numerical model, which included the usual terms, the distortion energy, surface energy, dielectric energy, and flexoelectric energy. It was thought that this was important for switching the sort of cells that we're interested in. So what we were interested in is a cell on a completely different scale. It looked rather like the one that someone was talking about in the last one talk, where we have a grating like this, so coming out of the board, so just a corrugation if you like, and a surface here, and homeotropic anchoring on both sides. Now in this case the length scales are, this period is about a micron, and this distance, as I said before, is about 4 or 5 microns. We get bistability. There are two possible states. One, which is just where the liquid crystal is largely vertical. It's matching the boundary conditions, but largely vertical. That gives a dark state or darker state. And the other one, where the liquid crystal, actually there are defects. There's a defect here and a defect at the surface here, which stabilize the state, which then tilts like this. And so it's quite, I seem to have missed a slide there. No, that's what I wanted to. So those are the sort of profiles that you get from the director model. And with the dielectric energy, this just depends on the electric field, but not on the sign of the field. So we can see that we can actually understand how to switch in this direction. The dielectric effect actually destroys these defects and gives us a vertical state, and then when we take the field off, it just relaxes the state on the left. But not at all clear how it switches in the other direction. So when we started, this was a big question: what's causing this? And the suggestion was that it's flexoelectricity. So as the material is distorted, there's a induced polarization in the material, and because of the polarization now, there is a direction here, then there'll be an interaction with the electric field, but that interaction will be different if the field is in this direction or in the opposite direction. So the question is, can flexoelectricity explain what we're seeing in terms of the switching? And so what we did was we looked initially at a gross simplification, which was to say, well, suppose we've got a flat surface, but the flat surface has got two stable anchoring conditions. So if we look at the anchoring energy, there's actually the function looks something like this. So there are two stable positions on this surface. This surface is just homeotropic. And can we just make that simple one-dimensional, effectively one-dimensional model, and can we use that to and see whether flexoelectricity can be explain what we see? And it turned out we could. This is work done by Andrew Davidson, University of Strathclyde. He's a case student with us, and on the left are some experimental results in terms of what we see when we do the switching, and these were the results from his model. And it did look as though the flexoelectricity could explain what we were seeing. But of course, that's a very coarse model, a very gross approximation. It was useful in terms of us getting some insight about what's happening, but the next stage was for us to develop a Q-tensor model, and we did that with Nigel Mottram, Strathclyde, and we were able to show switching, and that in this direction, the difficult direction, if you like, with the formation of defects somehow in the groove, and then the defects moving on the surface to give us our final solution, our final stable state. So again, the flexoelectricity did seem to explain and show us at least some of what was happening. And that was useful because we could then go to the liquid crystal manufacturers and say, we want a liquid crystal which has got a lower dielectric anisotropy, because there's a trade-off between the dielectric anisotropy, flexoelectricity terms, and which has got high flexoelectricity. And we were able to get a range of materials from them with those sorts of properties and find, in fact, better materials to use in our cells. So by understanding then what was going on, we were able to make some progress. So now to open problems. Well, that last model was a Q-tensor model. It's a finite element model, and it works well in one dimension. It works reasonably well in 2 dimensions, but in 3 dimensions it's far too slow, far too demanding at the moment. And so there are a number of questions. I've actually gone on to the second one there. Can we find an efficient formulation of a finite element model where we can get useful extensions 3 dimensions and use that to explore other configurations which we're interested in? And so that's really an open problem. At the moment, we're using Lagrangian elements, which are quadratic. Linear elements are no use whatsoever. We have to use quadratic elements at least, but even then, it takes far too long to run the models and get any useful results. It's also much more difficult to get convergence than in 2 dimensions. And to do any optimization in a 3-dimensional configuration, then we have to be able to run lots of different cells with lots of different configurations and consider the different results and see what's going to give us any benefit. And at the moment, certainly in 3 dimensions, that's not feasible. So that's one problem. The other problem was also touched on by Epifanio, which is what should we really do about the surface interactions with the liquid crystal? What's happening at the surface? We've used either rigid anchoring, Dirichlet boundary conditions, or something like the Durand and Nobly anchoring terms that were mentioned earlier. And while they do work, and that for a uniaxial material they actually reduce to the usual Rapini-Poplar anchoring terms that people use in a director model, there is some question about, is that the right thing to do? How should we do it properly? And how can we make progress there? Part of that, though, is I put as challenges for you as young researchers. Some of you will stay in academia. Some of you might go into industry. And so the challenges for any model are, how do you choose the appropriate parameters for your model? So for the Q-tensor model, for example, how do we know what elastic constant, what the equivalent of the elastic constants to use? How do we know what to use for a flexoelectric term? And so on. Now, what we've done there, and whether that's good or not, is to say, well, let's assume the material is uniaxial with the equilibrium order parameter, that is the order parameter set by the thermotropic energy, and the model then reduces to a director model, and we can get a direct comparison between our elastic terms in the Q-tensor model and the usual elastic constants, and similarly with the other parameters, and we can therefore say, well, if we assume that those carry over into the Q-tensor model, that gives us a starting point for the parameters. But there's always a problem for any model. How do you choose appropriate parameters? Once you've got a model, the other question is, how do you validate your model? For us, obviously it's important that what we're doing is going to give us results which are reliable and which we can then use to say, well, therefore what we need to do is change things in this way because we'll then get a better optics or we'll get better switching or something. But that will only be useful if we can be confident about the model. So what can you do to validate the model? What experiments can you do? Can you work with experimentalists? Can you get some validation for what you're saying in your model? And another challenge for you, perhaps certainly if you're working in academia, is bridging the gap between working at a university as a case student or as a researcher and working with industry, and being able to communicate, it's a rather strange spelling, be able to communicate your results to people in industry, to the experimentalists who've come to you and said, I've got this problem about interaction between colloidal particles in a liquid crystal. I think there might be something I can do there that will give me some benefit in terms of a liquid crystal cell or something. So what can you tell me about the interaction between these colloidal particles and the liquid crystal molecules? Will density functional theory give me any benefit? Can it tell me about the order of the large colloidal particles in relation to the order of the liquid crystal? How does that depend on the materials and so on? So a whole range of different things where somebody might come along and ask you, but then of course you've got to be able to A, understand what they're asking you to do, B, do it rather than solve some other problem which actually is much more tractable, but which doesn't really give an answer which the industrialist wants to know about. And even if you've got an answer from a model which is useful and appropriate, how do you communicate those results to someone in industry, an experimentalist who's not a mathematician, he doesn't know about gamma convergence or Sobolev spaces or any of these other tools that people use, but wants to understand what you've done and be able to see and learn from it. And the last thing, certainly, and I'll put the last one on there, quite personal, because if you go into industry, then I think you need to go into it possibly working on liquid crystals, because that's the experience you've got at the moment. But I think you'll then need to be flexible and not expect that you can work on liquid crystals in industry until it's time to retire. So I say that because I started at Hewlett Packard working on pattern recognition, and I did that for about 5 years, and the company then decided that they would rather we did some other things and they didn't want to spend their money on that anymore. Then I worked on liquid crystals and some of the work you've seen here, that lasted for about 15 years, and in August they decided that they weren't going to pursue that anymore. They wanted to do something new, and so I've now been working on something else on signal analysis, and in some ways some sort of pattern recognition as well to do with that, analysing the signals, so that's as the career's gone on. And in fact they've now announced that with a new head of HP Labs arriving 2 months ago or so, that in fact they don't want to work on that either, so something else to do. So I think if you go into industry, certainly flexibility is something else you need to be able to think of, be aware that that's what you will need to work in industry. There's no guaranteed working on liquid crystals, but perhaps it's the same in academia. Things change and focuses change, and you need to go where the funding is in some way, so perhaps there's some flexibility needed there as well. Right, so I hope that's been useful, certainly for the young researchers, in terms of what happens in industry, certainly in our industry, and what the challenges might be.
The most open problems concern liquid crystalline property, anchoring, Q10.
Yeah.
Does it mean that no problem to solve Maxwell equation, optical, electro-optical part?
Oh yes, no, there is certainly. For some of the cells, the sort of things we're experimenting with, you can use the Bowman sort of optical model, divide the cell into layers, and provided you have a sensible number of layers, you can calculate the optics. That's what I showed there, and that's quite straightforward. For some of the cells like these with the grating, then it is much more difficult, and you really do need to solve Maxwell's equations as well. And so part of the work we were doing until we finished in August last year was developing a finite element model, which was going to work, do the liquid crystal modelling, but then use the results from that to do the optics with.
You showed a slide where you had a plastic and you had a liquid, very thin liquid crystalline thing in there. How do you get that in there? I mean, how do you put the liquid crystal in there?
I'm not probably the right person to ask, because I don't do work in the lab, but for those sorts of cells, if I go back, for these sorts of cells, for example, then you take the plastic and you coat it with photoresist, and you then expose it to UV light. Well, that's a little bit. So you take the plastic, photoresist, you put on a mask. This is just a simplification, but you put on a mask and then you expose it to UV light. Parts that get exposed then become essentially soft, and you can wash them out. It's like developing a film or something. So then you develop it, and then these parts disappear, and what you're left with on the surface then is a grating. So that's the start, and then you need some spacing mechanism over about 80 microns, the sort of size of a pixel. So this obviously isn't a scale, these are about a micron, this is about 80 microns. And then you put liquid crystal in here, and then just squash it down. I think excess liquid crystal gets expelled, and then you've got your cell. That's essentially an outline of the process. There's a bit more subtlety to it.
The reason why I'm asking is because of your inverse problem. There's of course one way by which you probe it, which is looking at the scattering and then from there trying to test it. the data.
Yeah.
The other way you could approach the morphology here is to basically do a sort of fluid and fluid modeling as to how the morphology based on just a crystal, maybe if it's a pneumatic, then just pneumatic hydrodynamics,
Yeah.
and then from that predict what the structure looks like.
Right.
And maybe
Yeah.
match the
Yeah.
two.
Yeah, we certainly haven't done that, but that certainly would be a possibility. Yeah. Any other comments, questions?
Thank you again.
Okay.